Hi, welcome to this module, and in this module what we will learn? We will learn analog multipliers. So, we have seen several application of op amps until now. We have also seen a lot of experiments, right, and when it comes to analog multipliers, how exactly we can design analog multipliers. So, what are analog multipliers, and what kind of models are used to design those multipliers? That is what we will be looking at in the current module. So, if you see the slide, the basics of analog multipliers. When we say basics, what does it have? Analog multiplier is a circuit fundamentally having two input ports and an output port. We are multiplying two signals, let us say Vx and Vy, and we get output as Vx into Vy divided by k, where k can be a scale factor. So, in a very simple terms, if you see analog multiplier, we can say having two input ports and one output port. So, the signal at the output port will be a product of two input signals, and the circuit will have a scaling factor of k, which comes from the design of the circuits. We will see that circuit as well in the next slide. So, if both the input signals are voltages, the transfer characteristic is the product of two voltage, right, and divided by scaling factor, which is right over here, right. Since we have two voltages, the transfer characteristics can be the product of two voltage divided by the scaling factor k, and the scaling factor would have a dimension of voltage, right. This is what is shown here. So, if you go to the next slide, we see three different type of multiplier, and we can say that it is a multiplication as a 4-quadrant operation. So, what does it mean? From mathematical point of view, multiplication is a 4-quadrant operation. We know that this means that both inputs may be positive or negative, as may be the output. So, for example, single quadrant, if the two inputs are unipolar, the output should be unipolar. If for two quadrants, if one input is bipolar, second input is unipolar, the output would be bipolar. If for 4 quadrants, if one is bipolar, second is bipolar, the output will be bipolar, right. So, this is what we mean by the quadrant and the input and the relation with the output. So, some circuits used to make the electronic multipliers are limited to input signals of one polarity, then the multiplier will be a single quadrant, right. It is only single polarity, you can see here unipolar, unipolar, right. So, it is only one polarity, but if you talk about two quadrant one, then we have bipolar input and unipolar input. So, if a one signal is unipolar, but others have either polarity, the multiplier is a 2 quadrant one, and the output is also bipolar. For the 4 quadrant multipliers, thus both inputs bipolar as well as output. So, but the point is, when you use 4 quadrant multiplier, the complexity of the circuit design increases. Now, if you want to see a simple electronic multiplier or logarithmic multiplier, what we see here, right, is a computational relies on the fact that the antilog of the sum of the log of two numbers. That means, if you see x and y, and if you take a log of this and you again take an antilog, then what you have is x y, right. This is what is antilog of the sum of the log. So, you have to sum this log and then you do the antilog, then you have the multiplication factor. If you do the subtraction of this value and then you do antilog, you can have a division in the output, right. So, this is shown for multiplier and divider, but what are the disadvantages? The disadvantage here is the limited bandwidth and single quadrant operation. So, for that, a better type of multiplier is a Gilbert cell. So, what exactly a Gilbert cell? We need to see, and the disadvantage of this particular approach that you can see in the schematic is its limited bandwidth and single quadrant operation. So, let us see the Gilbert cell. The collector current of a silicon junction transistor and its transconductance are linearly related, as shown here, right, where you can see that the collector current and the voltage between the base and emitter, if you take a division of that, would be equal to QIC by KT, and where IC is your collector current and VB is the base emitter voltage, Q is of course your electronic charge and K is your Boltzmann constant. So, when you solve this equation, what you find is this would be nothing but 8.3 into 10 raised to minus 6. This is because you put the values of Boltzmann constant and electronic charge, and this will be Vy plus 0.6 times Vx at 25 degrees centigrade. Why this 0.6 is that? 0.6 is the voltage drop that you find in this circuit. Alright. So, this relation can be used to construct the multiplier which you can see here. So, you apply Vx here, Vy here, and you can multiply the signal and you get the equation which is right over here. But there is a catch, the circuit performs poorly. The reason is because the Y is the offset by VBE which changes non-linearly with Vy, and the X input is a non-linear as a result of exponential relation between IC and VBE, right. So, because of this reason this particular circuit will behave poorly. So, again if we see the final thing is scaling factor varies with temperature, because if you see here we have seen that this equation will work at 25 degrees centigrade, but the scaling factor would change if I change the temperature from 25 to 26 to 27 and so on. If I reduce it also, there will be change in the overall value. So, there are three factors that will hamper the performance of this particular circuit, which is our multiplier circuit, and the first one, like I said, is the Y input is offset by VBE, second is X input is nonlinear, and third one is the scaling factor. So, Gilbert devised a method to work around this limitation by working with current rather than voltages. So, if what he did is by using current other than voltages, so we can have logarithmic value of IC by VBE properties of transistor, and if you consider this particular circuit, you can see that in this circuit the we can use current instead of voltage, and the equation would be delta IC equals to delta Ix Iy and delta Iy by Ix. So, what exactly this circuit is? The X is the input for that takes form of differential current, and Y is the input which is a unipolar current, right. Then we have differential current X flows into the diode connected, right. Transistors and logarithmic voltages compensate for exponential VB by VBE by IC relationship, which gives us a linear transfer function which is given by delta IC equals to delta Ix and Iy divided by Ix. So, if you use current instead of voltages, then the point can be solved. The limitations of the earlier circuit can be overcome. So, the Gilbert cell is still only a dual quadrant multiplier, as we can see it is only dual quadrant, but if I want to make a 4 quadrant multiplier, what can I do? So, but by cross coupling two such cells and using voltage to current converters, we can convert it to a 4 quadrant multiplier, right. If I use two of such cells, because each cell is this guy here, right, but if I use two cells, then I can make a 4 quadrant multiplier. So, it is a very basic, and thus is a very basic necessity to understand the analog multiplier operation. So, whenever you want to understand analog multiplier, you have to understand a Gilbert cell operation, and if I want to use the multipliers with operational amplifier for arithmetic operations, then I can use this multiplier in a feedback as shown in the non-inverting and inverting stages, which is right over here, right, and we can see that the output will be the V1 by V2 into K, and here it will be minus V1 by V2 into K. So, following configuration we can use it for performing division here. This is because we are using the multiplier in the feedback. So, we can see that the multiplier will be V2 into VO by K, right, because the V2 is a voltage applied here, VO is output voltage, it will multiply and there is a factor K, and the output will be nothing but minus V1 by V2 into K. Same way, if you consider this particular circuit, the output will be V1 by V2 into K. So, if I use a TI board and I want to design a multiplier circuit, then in the TI board we have MPY634 analog multiplier IC, and the schematic of the ports for this IC are shown right over here, right. The details of way to connect the inputs to this IC, specific details of operation for the MPY634, and experimentation of how to connect the signals, right, and look at the output of the amplifier output of the multiplier will be shown now in the experimental session that will follow after this particular class. So, the idea is to understand that how we can use the TI board analog multiplier IC and what kind of signals we can apply at the input so that we can see the change in the output voltage. So, let us see how this can be done with the experiment, and for the experiment we will perform this experiment so as to make you understand that how we can use the TI board for an analog multiplier. So, basically what we understand is when we want to understand analog multipliers, you have to understand a Gilbert cell, you have to understand what quadrant you need to work on. Is it a single quadrant, is it a 2 quadrant, is it a 4 quadrant multiplier, and if you are using the multiplier in a feedback like what we have seen, it can use as a for the division division application as well, right. So, let us see how the experiment can be performed for the analog multipliers, and if you have any questions, please revert back to us, we will answer you through the forum.
We have seen the analog multiplier section of the board in detail, how it is working from a connectivity point of view and functionality point of view. Today in this section we will see how that is actually working while with external inputs. So, let me quickly recapitulate what we have learned. So, we are basically trying to understand the analog multiplier, how they work. So, if you remember the board, so you had the board, you had the DC-DC converter section here, and you had the analog multiplier section here. Let us call analog multiplier as AM here for quick reference. Now, the board had input of, as per expectation, the board's inputs were supposed to be plus 10 volt, minus 10 volt and ground, correct. So, today we will be seeing how the analog multiplier will work with an external signal. Instead of 10 volt, we will be giving plus 15 volt, minus 15 volt and ground to the board, and the board would work fine because it is within its tolerance level. So, it will work fine as we have seen in previous experiments. Before we start doing the experiment, let us just quickly see how the analog multiplier had worked. Okay, so if you remember the analog multiplier, so there was 3 sets of inputs x1, x2, y1, y2, z1 and z2. Essentially there was a adder here and this was getting added plus and this was getting subtracted. Similarly, and then this output was going to the multiplier, and there was y1, again there was an adder here, plus was there, minus was there, and this is plus, and the output was again going to the multiplier, and there was a scale factor here called 1 by SF, and all 3 of them were getting multiplied, and this Z1 Z2 was for something like an offset correction, that also you remember. What was happening? This is plus, this is minus, this output was coming and this was going to a amplifier with open loop gain of A, this was going to its positive terminal and this was going to its negative terminal. So, this is clear to you. So, what was the transfer function for this multiplier which we had discussed? So, basically what is transfer function? Transfer function is V out by V in. this would be V out. So, this is where your input voltages are applied. So, the V out expression would be V out is equal to x1 minus x2 into y1 minus y2 by SF minus Z1 minus Z2. There is no multiplication of Z1 because it is going directly to the inverting terminal of the op amp here, and these two x1, x2, y1, y2 we are getting multiplied here. So, this is V out. I guess this is going out of your view. I will just write it again clearly. So, this is V out. Okay. So, this is the overall scheme of how the analog multiplier is working. So, let us see how we are going to test it today. So, for simplicity purposes, today we will not be looking at how this section works, how this will provide for offset correction. We will only be looking at how basic multiplier will work here. So, let us see, we will simplify this again. Let me just clear the screen. Okay. So, basically without looking at op amp wise, what will be our function of the scheme of operation? X1 and minus x2 will be there, and y1 minus y2 will be there. These two will go to a multiplier and they will get multiplied with a scale factor, and we get the output, and this negative terminal would be grounded. So, we would get V out is equal to x1 minus x2 into y1 minus y2 by SF, which is a simple multiplier operation. Now, how are we going to test it? So, for again for a simplicity, the x2 where x1 minus x2 is coming, we will ground x2. So, x2 equal to 0 volt. We will ground y2. So, y2 equal to 0 volt. For to x1 we will give a sinusoidal signal, let us say of peak phi sin omega t, and we will give frequency is equal to around 1 kilohertz frequency we will give. We will try it out. Y1 we will give a DC voltage of around 3.3 volt, and this DC voltage we will generate by looking at the DC converter on board. This also we had covered when we introduced you So, when we introduced you to the board, we have discussed about the DC converter. So, when we are designing or when we are trying to design to test the multiplier, we should also take into account what would be the saturation voltage to which the output can go. So, here we are giving supply of 15 volt, right. So, the output voltage cannot go beyond plus or minus around 14 volt, which is a saturation voltage. So, when before we make a test plan, so how are we going to test a circuit? We should make sure that it does not go beyond the saturation value. So, here you see how would the circuit be. Now, we have further simplified it, right. So, because now x2 is 0, y2 is 0, and scale factor, what we have to do is scale factor is usually given as a voltage. So, scale factor we will again give our supply voltage only as 15 volt. Okay. So, what would happen? So, our V out would be is equal to x1 is what, phi sin omega t, which is around 1 kilohertz, x2 is 0 into y1 is 3.3 volt by 15 volt, because SF is our scale factor. Scale factor we are going to give a DC voltage of 15 volt. So, what would we get? We would get roughly this 15 would be 3. So, around 1.1 volt peak sine wave of 1 kilohertz frequency we are expected to get at the output of this analog multiplier. Let us see if this is working. So, before we start, first we have to see how we will make this 3.3 volt using the DC converter in the analog circuits board. So, let us just look into the board right now. So, this is the board. Now, we will zoom into the DC converter section. Let us see the DC converter section up close. Yes. So, we are going there. As you may remember, so this is the input voltage section, like what is the input voltage you want to give. So, if you want to give an external different voltage, you have this is a selection jumper selection pin. These 3 pins are the jumper selections. So, if you want to select from the board only, then you have to use a jumper between these 2 pins, bottom 2 pins, and if you want to select from an external voltage as the input voltage to DC converter, you have to select between these 2 pins. Now, here we have a LED display that shows you whether when the DC converter powers on. So, we have seen the DC converter section in the board before. So, we will just have a quick recap. So, this is the selector lines for the input voltage. So, there are 3 pins here, this is jumper selection lines. So, if you want to use the 10 volt from within the board, okay, then we have to select between the bottom 2 pins. Now, if you want to use an external input voltage, then we have to select between the top 2 pins. So, and once the input voltage is sufficiently large, then the DC converter detects that there is some input and this LED which is there gets powered on, that the LED powers on and shows that the DC converter is on. Now, let us power on the board. First we will see, we will not give any input voltage, we will just put a jumper selection for V in voltage, that the top 2. So, that means actually there is no input voltage. So, the DC converter should not power on, we will first see that. Now, first we will put the jumper before we power on. So, now we are putting the jumper from the top 2 pins for the V in. So, with this jumper put in place, so we have put a yellow jumper, you can see the metal part on top here, this metal part will short those 2 pins. So, it will, the middle pin is the input voltage to the DC converter, because these top 2 pins are shorted, it will take input from V in, but we have not given any input to V in. Now, if we power on, so we are powering on the board with 15 volt, but the DC converter is not powered on. Why? We have given input to the board, see here. So, here inputs are given to the board 15 volt. So, we can check if input voltage is there in the board. So, the power LEDs are on, that shows that the power is coming. So, we will just check what is the input voltage. So, as you can see in the multimeter here, it is 15 volt. So, input is there. So, now let us go back to the DC stage. Yes, we are in the DC stage. Now, because the input voltage in through this V in Berg nothing is given, DC converter has not switched on. Now, we will power off the board and then select the bottom 2. So, we will select the supply, that is instead of 10 volt we are actually giving 15 volt as we discussed before. So, we are powering on the board after giving the jumper setting as the supply from the board. So, now we are changing the jumper and we will give the middle bottom 2. So, now we have now we have given the bottom 2, right, bottom 2 pins as the selection. So, these 2 are shorted. Now, if you power on the board, you as you can just closely, so now we will switch on the supply to the board and closely observe this LED, you will see it coming to power. See, it has come up. Just let us switch off and switch on again, so that you see that this light is coming up. So, it will take some time for the LED to go away, because there are a lot of capacitors inside, because it is a DC-DC converter. So, it takes finite time to discharge. Now, let us power on the board. So, we are powering it on. After some finite time, this LED will power on. So, it takes some time for the DC-DC converter to come up. So, let us check the voltages and see how it is coming up. So, as you could see, the LED was coming. Let us just power it on now again, and let us just wait for some time. Yes, the LED is on now. So, this must see you see the delay, right. So, because there are a lot of big capacitors that are used in the DC-DC converter. So, they take finite time to charge and discharge. That is why this LED comes on and off. So, now once the LED is on, that shows that the DC-DC converter is up and running. Now, below if you see, you have the very important voltage out selection lines. What does this do? You can have two options for your output voltage. You can have 5 volt or 3.3 volt. Now, we have selected 3.3 volt, as you can see. So, your final selection will go out from the middle pin. So, if you select between these last two pins, you will select 3.3 volt. If you select from the first two pins, these two pins, you will select 5 volt. Now, we have selected 3.3 volt, and then 3.3 volt then will come as output, as the output voltage here. It will come as output voltage finally here. So, let us see what is the output voltage that is coming through these test points. We can measure through these test points itself. So, there is a test point for output voltage, there is a test point for ground. So, across the ground and the output voltage test point, we will measure, and you can observe in the multimeter what is the voltage that is coming. Yes, now, so as you can see, we are measuring the output voltage across the ground. So, we are getting 3.24, which is a reasonably good approximation to the expected value of 3.3 volt measurement. So, we were expecting 3.3 volt, we got 3.24 volt. Keep in mind, our input voltage was not actually 10 volt, we gave 15 volt, but the DC-DC converters are designed to work for huge voltage fluctuations. So, even when we are giving an extra voltage of 15 volt, still it is able to give us an output voltage of 3.3 volt. Now, let us just quickly switch off the power supply and select the other two, the next option, that is 5 volt, and see how much voltage output is coming. So, now we will change the jumper setting. So, now LED has gone off. The bottom jumper setting we will change. Now, we will select 5 volt, and then we will switch on the system. So, just wait for some time for the LED DC-DC on LED to switch on. So, that will ensure that the output voltage has stabilized. So, the LED is on now, as you can see, this LED is on. Now, let us see what is the output voltage that is coming now. Through the multimeter we will see. So, what is the output voltage in the multimeter? The output voltage so let us see what we actually got. We are given 5 volt selection. Okay. So, let us just see what in the section what it is. So, 5 volt we had chosen, and we have the power supply on. As explained, we have connected the multiplier. Okay. So what did we decide to test with? We thought we decided that we will do one input as a sine wave. Okay. A particular voltage and a particular frequency sine wave will be your x1 input, your x2 will be grounded, and y1 will be your another input, and y2 will be grounded. Okay. And we had discussed that we will be simplifying the multiplier by grounding Z1 and Z2, which is the negative terminal input, which is this one. Okay. And that we would be giving only the x pair, y pair, and seeing how the multiplication action takes place with the open loop gain. But I hope you have recognized the slight technical issue in that. The problem is that the open loop gain for any real life op amp would be such that obviously the output would be going into saturation, correct. Even though the multiplier action would be taking place, the output would go to saturation, because it's actually at the end of the day it's still an op amp and it's connected in the open loop configuration. So the Z1 and Z2 inputs, which we described as for used for offset, any offset corrections and all, is also also used for what is it? It is also used for giving the negative feedback to the whole system, so that you get your outputs with the closed looped gain. Okay. So I will be explaining this operation shortly. So before that, so you understood the whole concept of that, why we need Z1 Z2. It's for offset corrections and for the feedback control and for the correct multiplier operation, correct. So here if you look at the connections, so what are the main inputs we here? As we discussed, x1 will be there, x2 we will ground, y1 will be there, y2 we will ground, and scale factor will be there. For simplicity purposes, right now we are taking 1 by SF as 1, so we have not connected any input here. Okay. And if you look closely, so so this where the pointer is right now, this is x1 input, x1 and x2. So it will come x1 minus x2, but x2 we have grounded. Here you have y1 and y2, and we are having y1 minus y2, where y2 we have grounded. And here we have Z1 and Z2, Z2 we have grounded, and Z1 we have fed back from the output. Output is here. Okay. We have fed back from the output to Z2, Z1, and so we have the closed loop system and we have the inputs. So so that is the whole idea. Now because it is mathematically speaking, we have to understand that the multiplier mathematically multiplies two signals, correct. But when two signals, let's say two sine waves are multiplied, let's say A sin omega 1t and B sin omega 2t, if you do the math of it, you will know that the resultant signal will again be a sinusoid, but with the frequency of omega 1 plus omega 2 or omega 1 minus omega 2, depending on which all signals you have multiplied. Let's say you multiplied sine and cos, and you have A sin omega t and B cos omega t, and you know what sine 2 omega t is. What is sine 2 omega t? Sine 2 omega t is 2 sin omega t cos omega t. So if you are using the same frequency for both your inputs and you are multiplying it, you will effectively end up with a signal that has double the frequency of your input signals. So what is the multiplier essentially? The multiplier essentially acts like a frequency doubler or a frequency multiplier. It will act as a doubler if both the frequencies are same. Otherwise, it will just add up the frequencies of the individual signals. So for simplicity purposes, what we have used now, as we have explained before, we are starting off with one input as 3.3 volt DC, okay, and the other input as the sine wave of, let's say we are starting off with 1 kilohertz frequency, okay. Now even DC, so the DC signal has, what is the frequency of DC? DC has 0 hertz and the sine wave has 1 kilohertz. So mathematically if you do, you will get a very low frequency for the output signal. So that we will see the input. So let's see now let's look at the function generator once. Okay. So this is the function generator. So as you can see, we are using a sinusoidal signal of 1 kilohertz frequency. Okay. So that we will be giving, and now let's look at the power supply DC here. Okay. So we have given, so behind your board you can see the power supply here. So, and we have given 3.3 volt power supply here as another input. Okay. So, that inputs are given, you have seen the connections, I have explained the connections to you. Now, let us look at the output in the oscilloscope. So, the output we will see in the oscilloscope right now. Yeah. So, you can see the oscilloscope, correct. So, as you can see, we have stopped it. So, this run and stop is kept because the output is having a very low frequency. Remember, it is a frequency multiplier, correct. So, the output is still sinusoidal and the peak to peak also got multiplied with the 3.3 volt. Okay. So, the voltage levels are quite high, and as you can see the voltage scale is how much it is 5 volts, it is in the 5 volt scale. Okay. And so, what is the peak to peak fluctuation is around 10 volt here. We can see it is using 2 blocks. So, it is using 2 blocks here. So, it is around 10 volt swing, but I have stopped it because it is a very low. So, the time scale is around if you can see the time scale is 25 second time scale, that means it will capture the signal for 25 seconds. Okay. Let us just run it again, let us see what is happening. So, you can see slowly the signal getting generated. So, this whole window right will show a 25 second data capture. So, slowly you can see. So, let us wait for 25 seconds and see what happens. Slowly the sine wave is getting formed. See here, it is coming. You can see, right. So, what is this oscilloscope control, I mean the parameters that we have kept is such a way that it will capture the signal for 25 seconds. So, and the entire capture area would have 25 signals worth of data, and the voltage scale is 5 volt per division. Okay. So, it is around 10 volt swing. So, let us just wait for it to sweep through the entire let us keep looking at the oscilloscope while I explain. So, there has been a good learning, right. So, we have studied how the multiplier works. So, what are the inputs x1, x2, y1, y2, what is scale factor, and we can even have scale factor as 1 if you do not actually need a scale factor. Then what is z1, z2, why do you need that, and why if you operate it in an open loop condition. So, when you analyze it as a concept, even in open loop condition, you will get a output, but just that it will be saturated. So, you will just get a the DC level. So, for you to work in closed loop condition, you need to have a feedback back into your negative terminal. So, which signals are connected to your negative terminal? So, the signals connected to your negative terminal are the Z1 and Z2. Once this sweep is over, we will go back to the boards, writing board, and see this once again, and review, just quickly review what is it that we are discussing right now, why we need the feedback, and then we will go back and see. Now, we have used the DC signal as a sine wave, right. Then we will go back and apply a same 1 kilohertz sine wave of a particular amplitude as the input to both the ports, that is x1 and y1, and see if, so if you give the same sine wave, what happens? If you give the same sine wave, you get the doubled frequency in your output. So, that we will see, and also we will try to change the frequency and see how the output frequency is changing. With these next 2 sets of experiments, this section on multiplier we will close. Okay. So, as you can see, it has almost finished the sweep. So, it is like a 25 second sweep, correct. So, if you look at it, one sine wave, one whole sine wave has taken how much? So, it has taken around half of the entire display area. So, that is around 25 seconds, correct. So, around 25 seconds is one time period of the sine wave. So, what will be its frequency? Frequency will be 1 by 25 seconds. Okay. So, this is because we are applying a DC inside, and generally for analog circuits which work on frequency multiplication and all, DC is a slightly difficult signal to handle, but just for your understanding we have shown you this output. So, now this is clear. Now, let us see the screen. So, what we had? So, we had the multiplier section, correct. just quickly briefing it because it was all verbally spoken. So, in case people some of you are confused, I will just quickly go over it again before we show the both sine wave experiment. So, what we had? So, we had the x1 input, x2 input, we have y1 input, y2 input, we have the z1 input, z2 input, we have the scale factor, and you have the usual ground supply and all, and we have the mainly the output, correct. Now, how was the circuit connected? The circuit was connected in such a way that x1 would be there, x2 would be there, and then there would be an adder, correct. And this will be plus and this would be minus, and y1 would be there, y2 would be there, plus and minus, x1 x2, and both the outputs would go to a multiplier and you will have a scale factor. I am just going over it again. So, this should come to you automatically, okay, and this will go to the another op amp positive terminal, and the negative would have again your Z1 and Z2 plus minus, okay, and we would have the output there. So, but then this is still working in open loop configuration, correct. What is it working in? It is working in the open loop configuration. So, while working in the open loop configuration, whatever we give with a very small input signal also, we would finally end up in saturation. So, that is why in order to have control on the output, you need to have a feedback. So, for the feedback, what do you do? So, you will for simplicity, what we have done is we have grounded all the other pairs x2, y2 and z2 pairs, correct, and we have feeding back to z1. So, this is a negative terminal of the op amp, right. Inside there will be an op amp, no. So, inside there will be an op amp negative, it will connect here, correct, with this grounded. So, positive would be connected to these guys multiplied, x1 multiplied by y1 multiplied by scale factor, correct. So, this would come here plus output of this would come here plus, okay. So, we have connected feedback from the output to the Z1 terminal, which is the negative. So, that is why this is negative feedback. So, negative feedback is used for stable closed loop operation, right. So, if we connect back from the positive feedback output, again it will go to either a oscillating level or it will just saturate out. So, we have to have a negative feedback for the correct operation. So, that is why we use these terminals and also for any DC corrections, correct. So, it is clear to you. So, now next what we will do, as we have discussed, let us take a fresh page. Now, what we will do, we will have x1 also equal to 1 sine 1 kilohertz, okay, or sine wave of 1 volt peak to peak and frequency of 1 kilohertz. So, we will use the same x1 as y1, okay. So, let us try it with 1 kilohertz actually. So, and later, so first our starting frequency will be 1 kilohertz and then we would change it to 50 kilohertz also, okay, and see what is the output. So, we will see those two experiments. First experiment is what? First experiment is we are trying out with same signal of 1 volt peak to peak sine 1 kilohertz, same signal on both inputs and see what is the output, what are the output, what is the output we are getting. What is the next experiment? In the next experiment, we will change the frequency. And see how that change in frequency of the input, which is x1 and y1, is affecting the output. How is the output changing? Okay. And why all this while the V out would be fed back to the Z1 as the negative feedback. Okay. So, let us switch to the board and see the output. Okay. So, you have seen the board, the connections remain the same except that the y1 signal which was the 3.3 DC is now we have used same x1 input to the y1, Okay. So, we are not giving this 3.3 input voltage now. Okay. So, we are giving same sinusoidal input from x1 on y1. So, it will be two sinusoidal inputs which will be multiplied with each other. So, it will be the amplitude also remains same. So, now we are giving so though I explained that we will be giving 1 volt, for you to see it properly we are giving 10 volt peak to peak sinusoidal inputs, and because we have the closed loop feedback there, so it will not go into saturation. So, that will be taken care of. So, what is there? So, let us say the input is A sin omega t. So, omega remains same, A remains same. So, A sin omega t is getting multiplied by A sin omega t. So, A square sin square omega t. So, what is sin square omega t? Sin square omega t is 1 minus cos 2 omega t, correct. So, yeah, so a sin square omega t is 1 minus cos 2 omega t, is like proportional to, there are 1 by 2 and the a also comes, but fundamentally what we are trying to tell is sin square omega t translates to 1 minus cos 2 omega t, by 2 would be there, but that you can ignore right now. What we are looking at is the frequency component. So, sin square omega t's frequency is omega, while cos 2 omega t's frequency is 2 omega. So, you should get a double frequency on your output. Okay. So, let us see. So, let us see first what is the input that we are giving in the function generator. Okay. This is a function generator. Yes. So, we are giving 1 kilohertz. So, we are giving 1 kilohertz signal, okay, and 10 volt peak to peak, okay, sine wave. So, now we will see the, so connections and all remain same like we have explained, what we have explained before. Let us see the output. So, in the output we have shown you both the input signal and the output signal. The input signal is in channel 2, which will appear as blue in color for you, and the output signal is channel 1, which will appear as yellow in color for you. So, let us see the oscilloscope. Okay. So, now we have the input and output here. So, it is very clearly visible to you the input, see the input is the blue. So, it is shown as 1 kilohertz, it will show do the frequency measurement. So, here blue color, if you see it is around 1 kilohertz, here around 990 hertz, which is 1 kilohertz, around 1 kilohertz, okay. And the yellow, the frequency, yellow is the output, clear, this is the output, and yellow is shown as 2 kilohertz, correct. So, we are seeing the frequency doubling operation. Also, looking at mathematics, if you see it very clearly, we saw that sin square omega t translates gets proportional to 1 minus 2 cos 2 omega t, correct. So, there should be a 90-degree phase shift in your output. So, that if you look at the middle line, you will be able to see that there is a phase shift here, okay. So, 1 minus cos 2 omega t will come, 1 is actually what, 1 is 180 degree. So, you will get around 90-degree phase shift here. So, which is what you are seeing. So, this blue is starting from 0, while yellow is starting from the midpoint. So, that is a 90-degree phase shift. So, the 90-degree phase shift also you are seeing between the output and the input. So, very clearly it is that whatever we are saying in mathematics, we are like on analyzing the signal, we are actually seeing it practically working. That is a fundamental goal of this course. So, let us see. So, let us change the frequency now and see what happens, okay. So, it was 1 kilohertz, I am making it 2 kilohertz, accordingly the input has changed and the output also has changed. So, let me keep increasing it, you can see the frequency changing nicely following the input and the double relationship is maintained. This is the second experiment that we plan to do, correct. So, if you see, so the frequency is changing, just keep looking at the frequency column here, okay. So, the input is 10 kilohertz, output is coming as 20 kilohertz, correct. Again input is 11, 22, 12, 24, 14, 6, 17, 34. So, it's like nicely following. So, this is a multiplier operation, we are seeing both the amplitude multiplication and so the amplitudes are not shown and same scale for both, because we wanted to show you both signals. So, but more importantly the multiplier is mainly used for the frequency multiplication, because that finds lot of application in communication systems like for frequency modulation, amplitude modulation, in those applications multipliers are used. So, that is one place where these analog circuits are used in the analog front end of communication systems. So, they are used in a lot of places. So, multiplier is a very important circuit block that you can use very nicely for your analog circuit applications. Hope this module was helpful to you. See you soon.